prehistoric huts, Viking longhouses, suburban homes. Humans have always loved burning things to keep them warm. Unfortunately, burning fuels for heating now accounts for around 10% of global carbon emissions. So, humans will never cool the planet unless they stop playing with fire. But what if there was another way that avoided burning things altogether? What if you could pull heat energy from the air, water, or ground outside, warm an entire house with it, and still have enough for a hot bath? And what if you could do it with fewer carbon emissions and lower costs than conventional heating? Humans normally generate heat by burning things, but heat energy is everywhere, in the air, in the water, and in the ground. It might not feel like it, but even when it's below freezing, some heat is still there. And best of all, it's free. So how do you capture it? Well, a clever chap called Rudolf Clausius
Guten Tag.
described the basic principles of heat transfer back in the 1850s. He showed that heat energy naturally flows from hotter spaces, like a steaming cup of coffee, to colder ones, like the winter air. And if a glass of icy water is colder than the air, the heat will flow from the air to the glass, warming it up to melt the ice. Like a hot cup of coffee, when you heat a home, it constantly loses warmth to the cold outside. Not ideal. But what if you could reverse the process, pulling heat from outside into your home, even in winter? Sounds impossible, right? Well, that's exactly what 180 million heat pumps are doing today. But instead of using ice, heat pumps use an extremely cold refrigerant fluid to absorb heat from air sucked in by a fan. Since the refrigerant fluid is even colder than the air, it easily absorbs any heat, and as it warms up, it vaporizes into a gas. But this gas is still relatively cold, so how does it heat up a house? Well, that's where a compressor comes in. By squeezing the gas and its heat energy into a smaller space, it gets extremely hot. And once it's hot enough, the heat flows into the house. The energy can also be transferred to a water tank to provide hot water for your radiators and steamy baths. Finally, as it releases heat, the refrigerant condenses back into a liquid and expands through a valve, cooling it enough to start the cycle again. So while it seems like magic, it's just physics. But fans and compressors both use energy, so why not just use that energy to heat your home directly? Well, with conventional gas or electric heating, it takes 1 unit of energy to generate a maximum of 1 unit of heat. Heat pumps are different. Because they take heat that's already there, the same unit of energy can move 3 to 5 units of heat. This makes heat pumps 3 to 5 times more efficient than gas or electric boilers, because they move heat rather than create heat. Better yet, in the summer, many heat pumps can work in reverse, providing air conditioning to keep cool. Best of all, they can cut energy costs, reduce demand for fossil fuels, and reduce carbon emissions by 30% or more. If you power them with renewable electricity, they could even eliminate the emissions from heating altogether, potentially saving billions of tons of CO2 worldwide. But there are even better ways of getting heat than pulling it from the air. Take the ground, for example. Not only are ground temperatures more stable throughout the year, but in winter the ground is often warmer than the chilly air above. So, although it's costly up front, installing pipes underground makes it easier for heat pumps to absorb heat, improving both efficiency and running costs. But there's another source of heat that's even better than both the air and the ground: water. Since water transfers heat incredibly well, running pipes through a body of water like a large lake or pond provides a reliable source of accessible heat. And while installation can be just as tricky as ground source heat pumps, they are an excellent choice, particularly for large commercial buildings. Clearly, heat pumps have huge potential, but there are some drawbacks. First up, refrigerant fluids. If they escape into the air, they have a powerful greenhouse effect that can be over 2,000 times worse than CO2. But with proper handling, the benefits of heat pumps far outweigh these risks. And new, less harmful refrigerants are already in development. The next issue is location. Not every home is heat pump friendly. Not only do heat pumps typically need space for an outdoor unit, but to work optimally, they're best paired with modern, well-insulated homes. And then there's the cost. Installation costs can be expensive in the short term, but over the long term, heat pumps offer consistent savings in energy costs. And depending on the system and the local price of electricity, they can pay for themselves in around 5 to 15 years. Better yet, as renewable electricity continues to get cheaper, so will the heat pumps that run on it. Many countries also offer grants, schemes and subsidies that significantly reduce upfront costs, in some cases by over 90%. Last but not least, there's the question of extreme cold. While most heat pumps work fine in icy conditions, below -25 degrees Celsius, they can struggle. But backup or hybrid heating systems can be used in particularly harsh winters. Luckily, temperatures that low are rare, so heat pumps are suitable for most climates. In fact, cold Scandinavian countries take the top 3 spots with the most heat pumps per household in the world. Thanks to clever government foresight, 60% of Norwegian homes now use heat pumps as their primary source of warmth. So, with government help, a bit of planning, and the expansion of renewable electricity to power them, heat pumps could finally replace burning things for warmth and take a huge chunk out of global emissions in the process. Please spread the word about climate change solutions by sharing this video and like and subscribe if you would like to see more. Thank you.